So here we are, the way that this class will look for the rest of the semester. It's my PowerPoint that I would typically present in class, and I'll write notes on the slides. You can also hear my voice and take notes from my voice. I'm not going to write everything on the slides, and I'll probably write them in shorthand, but this is what the class will probably look like, right? I'll try to post a number of these on the days we would typically have class. I really apologize today. Obviously, the first trial, I had some profound technical difficulties, but I think I've worked through them, so I'll do the best that I can, and I ask that you do the same. If you have questions about how everything will run, please let me know. Again, my apologies for not getting these up more sooner. I'll continue to work on it so we cover the content that we need to cover to meet the course learning outcomes. With that, we're working in Chapter 6, and so we'll get started. And I want to pick this up based on something I said last class and give you some more information. And I think it's a good place to start our review before we begin new information. So we had talked about the acetylcholine receptor and, there's a nicotinic or ionotropic type of receptor that directly gates an ion channel, but there's also this G protein coupled receptor. And I gave you some details about it, right? Talked about the binding sites and the helical membranes and those things. I told you that there were multiple types, and I don't think I gave you enough context. So I mentioned that binding causes the G protein, right? So you have acetylcholine that's bound here, and that activates this G protein, which typically associates with this domain down here. So you could imagine a G protein here. And that this can go on to have a bunch of different effects indirectly. Right? This isn't going to activate an ion channel, but its effects are going to be indirect. I mentioned one effect was that it's going to activate inwardly rectifying potassium channels. Right? So one of the effects of this G protein, right, when the ligand is bound, is this is going to go off and target something else. And one of the things that it targets are these inwardly rectifying potassium channels. It's abbreviated KIR. Right? So this is an inwardly rectifying potassium channel. So no voltage would gate this inwardly rectifying potassium channel. It needs to have this G protein associated with it. And when the G protein activates this KIR channel, this inwardly rectifying potassium channel, this is what we see, right? I think the best way to do this would be to draw the relationship between current and voltage. So on this axis, right, I'll have my current represented with the letter I. And on this axis, I'll have my voltage, the voltage of the cell's membrane. Okay, so where they cross would be 0, minus 20, minus 40, minus 60, minus 80, minus 100, minus 120. Right, and on the other side, we'll have 0, 20, 40, 60, and so on, okay? And current, we can just think of current as in terms of relative amounts, right? So if this is 1 unit of current, this would be twice as much, 3 times as much, and of course, upward would be representing current going out of the cell, while downward would be current that's coming into the cell, right? Potassium carrying current. Remember, right, that EK is somewhere right around, in here somewhere, right? EK is probably minus 90 or something. And so when these inwardly rectifying potassium channels are active, what we see are at very, very hyperpolarized potentials, very, very hyperpolarized, steep inward potassium current. Right? So if we were to set the cell, to give the cell a voltage shock to, minus 100, we get a large inward potassium current. Right? That's typically unusual. Why? Because we're trying to get to EK. And what we see is that these currents hold the cell typically pretty close to EK. Right? You would imagine that, if the cell was then depolarized, right, where you would expect voltage-gated channels to allow potassium out, this inwardly rectifying channel that's mediated by this G protein, right, which interacts with this inwardly rectifying channel at voltages that are pretty hyperpolarized, is going to keep the voltage of the cell right around, its EK value, right? Now, what happens when the voltage of the cell is increased and these channels are active, right? So say these channels get activated and the voltage of the cell is, I don't know, minus 60 or minus 40. We see very little outward current, right? To the point where there's really no outward current whatsoever, no current at any voltage that's more depolarized, okay? So these inwardly rectifying potassium channels are active. Oops, that'll happen, I apologize. They're active at very hyperpolarized potentials. This is supposed to say hyper. Right? Typically what they do is they hold the cell near EK. Okay? And so this means that even if the cell is stimulated, but the G protein is activating these inwardly rectifying channels, typically no action potential will be given because these channels have such a large current of potassium that's actually flowing into the cell to keep it at EK. That's why it's inwardly rectifying towards EK. There's very little outward potassium current that they pass. Right? So when we think of voltages where potassium would want to leave the cell, what we see right here is that it does, but only in a little, in very small amounts. And by the time we get to these very depolarized voltages out here, there's basically no permeability, no conductance of these channels, and as you can see, no current that passes. So that's how it mediates its inhibitory effect. It basically locks the cell, right, in this state, holding the cell near EK in a pretty hyperpolarized potential. So even if there are other voltage-gated channels that you would think would take the cell this way, right, as potassium would leave the cell and it would want to change its membrane potential towards the positive, that's not what happens, right? We get locked in here. Another way to think of how these inwardly rectifying channels work is if we looked at a conductance plot. Okay, so again, if we put conductance, if we made our conductance over here, just relative, right? So this would be like 100% conductance, permeability, and this would be 0%, right? Like no permeability whatsoever. And we looked at how this worked with respect to voltage, right? So we might have 120, I don't know, minus 80, minus 40, 0, 40, right? So this is the membrane potential of the cell. So this is in millivolts, right? These channels, these inwardly rectifying that are bringing potassium into the cell, right, are very active, right? Highly conductive at 120. And they get substantially less active as the cell depolarizes, right? So again, if the resting membrane potential is somewhere in here, and these channels are active, right, what's going to happen is in order to get back to this value, in order to get to EK, potassium will want to come in, and that's what happens, right? That's why we see this downward deflection on this graph. So these are highly conductive at minus 120, but they are not very conductive at other voltages, right? And so we see this sort of curve here. So by the time we get to voltages more positive to EK, right, everything in, say, this space, there's very little conductance. Conductance, of course, is G, right, our conductance value. So not much current is going to be passed. The majority of the current is going to be passed at these hyperpolarized potentials that allow potassium to come in and get us back to EK. A second effect that activation of this G protein here can have, right, that this G protein here has, right, is it can allow calcium to come out of intercellular stores and raise intercellular calcium levels And raising intracellular calcium activates another type of potassium channel. Activates calcium-gated potassium channels. So in this case, if we draw, current here, and maybe we draw time here. So this is not going to be volts, but so here's our current, and this is over time. And we take a control cell, right, with its normal low levels of calcium, and we take that cell that's at resting membrane potential, and we give it a voltage step, right? We give it a voltage step for some amount of time, right? So maybe this is the time that we give it the voltage step. And we're going to increase the cell's resting membrane potential in a patch clamp situation. We're going to go from whatever it's resting at, minus 70 or minus 65, and we're going to take it to plus 50. Now, under normal conditions, you would think about what that does, right? Well, potassium would like to be, minus 90. And so opening potassium channels allows the positive charged potassium ion to leave the cell. And that's what happens, right? Even at sort of physiological calcium, these channels, these calcium-gated potassium channels here, we do see some amount of potassium, right? I don't know why I drew an arrow here. Right, some amount of potassium leaving the cell until the voltage step goes away and the cell goes back down to its rest. Outward flow of ions, meaning we're trying to get to that EK value. Right, so this was be at normal calcium in the cell. Okay, but if we were to take this G protein, right, activate the G protein coupled acetylcholine receptor, right, binds here, the G protein becomes active here, allows intracellular calcium to rise. Now, if we give the cell that same voltage step, we get substantially more substantially more potassium that leaves the cell, right? So we would get something that looks like this. So this is high calcium. Now again, what I drew here is not the current of calcium. This is the normal calcium level within the cell, and this is the high calcium level that's mediated by the acetylcholine receptor, by this G protein coupled acetylcholine receptor, right? Raising the calcium level means more positive current that flows out of the cell toward EK than at the normal levels, right? Okay. So the second type of channel here, besides those inwardly rectifying potassium channels, are these calcium activated. Potassium channels. Think about what the conductance would look like in a graph that we had where I asked you to diagram the conductance of these potassium channels at different calcium levels, right? So say we did a similar thing where I had, on this line, I had the conductance, and on this line I had the membrane potential down here, right? So in millivolts. Millivolts, right? So it's membrane potential, and say we were looking at this from, anywhere for voltage steps from minus 100 to say minus 50 to 0 to say plus 50. What do you think those lines would look like? What do you think that the conductance, did I write current? My mistake. I want the current here, the G. Permeability, right? How would this look under low calcium? And how would it look like when these calcium-activated potassium channels were active? That is, under high calcium conditions. What would those curves look like? Sorry about my left-handedness, that keeps happening. Okay, we're going to move on to new stuff now, but this was just to remind you of different effects that could be mediated by this particular G protein coupled receptor.